The content in this presentation is covered on pages 116 through 127 of your textbook, and it's meant to help you achieve learning objective number 28, which is to identify the basic types of fog and describe how each one forms. Be sure to skim pages 116 through 127 before watching the video, and be sure to read the chapter carefully before you attempt the online quizzes. Fog is defined as a cloud with its base at or very near to the ground. Physically, there are no differences between fog and a cloud. Their appearances and structures are the same. The essential difference is the method and place of formation. So while clouds result when air rises and cools adiabatically, fog results from cooling or when air is becoming saturated through the addition of water vapor. Although fog is not inherently dangerous, it is generally considered an atmospheric hazard. During daylight hours, fog reduces visibility to 1 or 2 miles. When the fog is particularly dense, visibility may be cut to a few dozen meters. So, 36 feet would be as thick as I think I've ever seen it. But making travel in those conditions, very difficult, very dangerous. Official weather stations report fog only when it's thick enough to reduce visibility to less than about a half mile. When the temperature of a layer of air in contact with the ground falls below its dew point, the condensation that results produces that fog. So depending on the prevailing conditions, fogs formed by cooling are called either radiation fog, advection fog, or upslope fog. Radiation fog results from the radiation cooling of the ground in the adjacent air. Usually it's a nighttime phenomenon that requires very clear skies and high relative humidity. Under clear skies, the ground and the air immediately above cool rapidly. Because of the high relative humidity, a small amount of cooling lowers the temperature to the dew point. So if the air is calm, the fog is usually patchy and less than 3 feet thick. For radiation fog to be more extensive, in the vertical direction, you need a light breeze. So a wind of 2 to 3 miles per hour is enough, but it's required to make enough turbulence to carry the fog upward to 30 or 100 feet without dispersing it. High winds, on the other hand, mix the air that's forming the fog with the drier air above it, and the fog is dispersed. So we need a light breeze, not a wind, but a light breeze. Because the air containing the fog is relatively cold and dense, it flows downslope in hilly terrain. As a result, the radiation fog is usually thickest in the valleys, whereas the surrounding hills may remain clear. So we see this all over the Pacific Northwest. Once we're up in the Cascades, we'll see foggy bottoms and clear tops all the time. Normally, radiation fog dissipates within 1 to 3 hours after sunrise. And it's often said to lift. However, the fog doesn't actually lift. Instead, the sun is warming the ground and the fog disappears from the ground upward. Advection fog happens when the warm, moist air blows over a cold surface. So it's chilled by contact with that cold surface below. If there's enough cooling, you'll form a blanket of fog called advection fog. And the term advection refers to air moving horizontally. A classic example is the frequent advection fog around San Francisco's Golden Gate Bridge. The fog experienced in San Francisco, as well as many other West Coast locations, is produced when warm, moist air from the Pacific Ocean moves over the cold California current. A certain amount of turbulence is needed for proper development of advection fog. So typically a wind between 10 and 30 kilometers, so that's 5 and 15 miles per hour, usually are required. Not only does that turbulence facilitate cooling through the thicker layer of air, but it also carries the fog to greater heights. So advection fogs often extend 1,000 or 2,000 feet above the surface and persist longer than radiation fogs. Advection fog is very common at this famous Washington State location. This is Cape Disappointment, which is known as the foggiest location in the United States. The station averages 2,552 hours of fog each year, and that's equivalent to 106 days. Advection fog is also a common wintertime phenomenon in the Southeast and Midwest when relatively warm, moist air from the Gulf and the Atlantic moves over cold and occasionally snow-covered surfaces to produce widespread foggy conditions. This type of advection fog, though, tends to be thick and does produce hazardous driving conditions because it's known to cause freeze on contact with the ground, making black ice. Upslope fog, as its name implies, is created when relatively humid air moves up a gradually sloping landform, or in some cases up the steep slopes of a mountain. Because of the upward movement, air expands and cools adiabatically. If the dew point is reached, an extensive layer of fog will form. It's easy to visualize how upslope fog might form in that mountainous terrain. However, in the United States, upslope fog also occurs in the Great Plains when humid air moves from the Gulf of Mexico towards the Rocky Mountains. You may have heard that Denver, Colorado is known as the Mile High City, and that's because it's 5,280 feet or so above sea level. The Gulf of Mexico is, of course, at sea level, so air flowing up the Great Plains expands and it cools adiabatically by as much as 22 degrees Fahrenheit. And that can result in extensive upslope fog in the Western Plains. When saturation occurs primarily because of the addition of water vapor, the resulting fogs are called evaporation fogs. So we're not changing the temperature here. Mostly what we're doing is adding moisture. Two kinds of evaporation fogs are recognized here. Steam fog is one of them, and frontal or precipitation fog is the other. So when cool, unsaturated air moves over a warm water body, enough moisture may evaporate to saturate the air directly above. And that generates a layer of fog. The added moisture and energy often makes the saturated air buoyant enough to cause it to continue to rise. And because that foggy air looks like steam that forms over a hot cup of coffee or tea, the phenomenon is called steam fog. Steam fog is a fairly common occurrence over lakes and rivers on clear, crisp mornings in the autumn, when the water is still relatively warm, but the air is comparatively cold. The steam fog usually forms a shallow, foggy layer because as it rises, the water droplets mix with the unsaturated air above it and evaporate. In a few settings, steam fogs can be dense, especially during the winter, as cold air pours off the continents and ice shelves over the comparatively warm open ocean. The temperature contrast between the warm ocean surface and overlying cold air mass has been known to exceed 50 degrees Fahrenheit. The result is thick steam fog, produced as the rising water vapor saturates a large volume of air. Because of its source and appearance, this type of dense steam fog is sometimes called Arctic sea smoke. Frontal or precipitation fog form along frontal boundaries where warm, moist air masses rise up over cooler, drier air. That is enough to generate a frontal fog. The foggy conditions result because the raindrops falling from relatively warm air above the frontal surface evaporate in the cooler air below, causing it to become saturated. Frontal fog, which can be quite thick, is most common on cool days during extended periods of light rainfall. The frequency of dense fog varies considerably from place to place. As you might expect, fog incidence is highest in coastal areas, especially where cold currents prevail, like along the Pacific and New England coasts. Relatively high frequencies are also found in the Great Lakes region and in the humid Appalachian Mountains of the eastern United States. In contrast, fogs are rare in the interior of the continent, especially in the arid and semi-arid areas of the West. So those are the areas in yellow here in this map. And I'm sorry about it being so out of focus. Maybe that's my eyes. But you can see up in the Pacific Northwest, we have all over the Cascades and the Olympic Peninsula, 80 days and more of foggy weather per year. And you can see maybe a little tiny bit of purple there in the San Francisco Bay. But a lot of advection fog on that coast and in most coastal areas. So use the course content provided on the Canvas site as well as outside internet sources to verify that you can formulate answers to these questions. If you can comfortably answer them, you're in great shape for the next test. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.